Everybody, let's talk about cutoff. So we already found that we had this infinite superposition of allowed modes within my waveguide. So we're going to write this down as, remember, beta sub n is equal to the square root of k squared minus gamma sub n squared. So recall that gamma sub n is equal to n pi over d, and n can just go from 1, 2, 3, all the way out to infinity. So normally what kind of happens is this difference here is going to be positive. So you have you have k, which is equal to omega over c, will generally be greater than gamma sub n under many conditions. But eventually, this n can be arbitrarily high. I can just keep going higher and higher, and eventually I'll reach a point where this condition no longer holds. So what happens in the condition where k is actually less than gamma sub n? So you look up here in this particular expression here, and you'll see I get the square root of a negative number. So what are the effects of that? So let's pick out a single mode from the infinite superposition of possible modes in my waveguide. So I have e of y comma z. Remember, this is polarized in the x direction. I'm going to say a sub n. I'm going to write this as like the nth mode here. Sine of gamma sub n y e to the minus j beta sub n z. So I'm singling out the nth mode where n is just some arbitrarily large number. Let's say it's like 50 or 500 or something, right? Eventually I can go as high as I want, and eventually I'm going to reach a point where this number here gets bigger than this, and I have to make sense out of that somehow. So let's write this out as follows. I have beta is equal to the square root. I'm going to factor out a negative 1. Gamma n squared minus k squared, like so. And that's going to become j times the square root of gamma n squared minus k squared. So I'm going to impose the condition here that gamma n is greater than k, so that this little radical here is now going to be some positive number. And this is going to be just some plus or minus j. And I'm going to give that a name. I'm just going to call it alpha, because why not? Okay, so what happens is when this condition is satisfied, I can only solve this radical as an imaginary value. Okay, so this alpha is just the square root of this difference, but now I have this j here. So what does that mean for my mode here? Well, we write it out like this, and it's tempting to imagine some mode propagating along with some kind of phase dependence here along z. But if I now take this value here and I substitute it into here, what happens? You basically get a mode with the following solution here. So let's write this out. I'm going to get an a sub n sine of gamma sub n y e to the minus j. And now I'm going to suddenly get a j alpha z, like so. So these j's are going to basically kill each other, and I'm just going to get an e to the, and remember this is still plus or minus, right? So I'm going to get e to the plus or minus alpha z here in place of that exponential. So instead of having a complex exponential implying some kind of sinusoidal phase variation along g or along z, I'm going to get just a real exponential, and it will either grow or decay. Well, obviously exponential growth is not a physically realizable solution because we need to have finite energy in the universe, but the exponential decay is potentially a finite solution. So we're going to throw away the positive term here and keep the negative as a viable solution. So what you essentially get is a sub n sine of gamma sub n y e to the minus alpha sub n. So I guess I should put a little subscript n here to correspond to the nth gamma here, times z. So I just get a real exponential decay in my mode, and it will just continually exponentially decay as n gets bigger and bigger and bigger. So the idea is for small values of n, I potentially have a real value for beta and a just nice sort of phase wavy propagation along z. But eventually as n gets bigger and bigger and bigger, this radical suddenly is no longer satisfiable with real numbers, and it has to have an imaginary value, and I get an exponential decay. So these are called evanescent waves. And I think it's an ENT, it might be an ANT. So I hope I'm not misspelling that. Evanescent modes / waves, okay, for something like that here. So they're evanescent in the sense that they still satisfy the wave equation, but they're not really waves in the strictest sense. They're these things that just decay and don't really carry any real energy or power in them. And we'll prove that in a little bit, that the actual power carried in this is 0. So there's actual energy in the fields, but it's more like capacitive energy. It's sort of stored there, but it doesn't carry any real energy down the waveguide. So you remember, this is the condition here. Gamma sub n is greater than k. So anytime this condition is satisfied, I will get evanescent solutions that carry no real power. So for that reason, these are also called cutoff modes, in a sense that they cut off the flow of power. So we're going to characterize that a little bit. So we have n pi over d is greater than omega over c. Then I am in cutoff in this condition. So I'm going to write this as 2 pi f over c. And then we're going to do a little bit of rearrangement, and we'll solve for f. I have f less than n times c divided by 2d, because the pi's cancel. Okay, and in fact, this is a less than or equal. So these are frequencies, you would say these frequencies are in cutoff. And in particular, if you equate them, f sub c is equal to nc over 2d, or since c, remember, is n over 2d, we're going to put the square root of mu naught epsilon naught for a waveguide that has no dielectric materials in it. So this is called the cutoff frequency. Okay, so we'll just write this here. Cutoff frequency. Like that. So what it says that if I have some parallel plate waveguide and I excite it at a very, very low frequency, eventually it will not carry any real power down the waveguide. It's kind of like waveguides are like these mechanical high pass filters, you could say, because if the frequency is too low, no real energy will go down the waveguide. And that should kind of make intuitive sense, right? So I'm going to draw a little waveguide here, like so. In fact, let's draw it on a new sheet of paper. So here is a waveguide, like so. And remember, this just kind of goes off forever down to infinity. So you can imagine a very, very high frequency wave, like a little laser beam, will eventually just kind of propagate down back and forth inside this wave. And that particular wave here, if you were to do the math on it, is actually a solution to the Fourier series of my infinite summations here. But now you take this exact same waveguide and imagine just a gigantic, huge wavelength striking that, right? So you could say, let's suppose this is like a millimeter in length here, and this wavelength over here is a full meter. Eventually, it should make sense that no actual energy should get in there. That for all practical purposes, this is just like pinched off and not going to allow anything to get into it. So there is a definite point in the geometry where this waveguide will cease to allow any energy into it because the frequency is just too low to create a propagating mode. Right, so that's kind of an intuitive visualization of cutoff. All right, so you have this condition here. Frequencies, anything below this condition here is too low in frequency and it will not carry real power through the waveguide. So a cutoff frequency or cutoff modes, evanescent modes, evanescent waves.